Ideal gas. An ideal gas is a mathematical model created by scientists to help predict and explain the behavior of real gases, such as hydrogen, oxygen, carbon dioxide, and others. The ideal gas in this mathematical model is given properties as listed from A1 to A6. With these properties, the ideal gas can be described by the ideal gas equation of state, PV equal to nRT, or PV equal to nKT. As it turned out, real gases behave like ideal gases when they are at low pressures. At moderate pressures, real gases behave approximately like ideal gases. The Avogadro number. A pair of shoes refers to two shoes. A dozen eggs is the same as 12 eggs. We are dealing with a very large number of molecules when dealing with gases. Therefore, scientists invented the Avogadro number, which is 6.02 times 10 to the power of 23. So saying one mole of molecules is the same as saying 6.02 times 10 to the power of 23 molecules. Lecture example 4, show numerically that K is related to Avogadro number. So the equation of state is defined as either PV equals to nRT or PV equals to nKT, hence K equals to N over nR divided by N, or R divided by Avogadro's number. So we get K equal to 1.38 times 10 to the power of minus 23 joules per Kelvin. Lecture example 5. So the initial state is given by the left diagram, and the final state is given by the right diagram. So A, state the equation relating the initial and final pressures, volumes, and temperature of the gas in A. So PV equal to nRT, so we get PV divided by T equal to N. So P initial, V initial, and T initial will be equal to N. P final, V final, and T final will also be equal to N. Hence, we got this relationship. And putting the numbers together, we get equation 1. So for part B, we use the same relationship and we get equation 2. For part C, we now have equation 1 and equation 2. Now, the insulating piston is at equilibrium when they are at the initial and final state. So for initial state, the pressure in chamber A will be equal to the pressure in chamber B. So for final state, it's the same thing. The pressure in chamber A will be equal to a pressure in chamber B. Now, suppose the pressure in A is larger than B, then the piston will move until they are the same. So when they are at equilibrium, the pressure has to be the same. Equation 2 divided by equation 1, and substituting 3 and 4, we get x equal to 0.05 meters. Molecular interpretation of pressure. This topic is included in O-level physics. At A-level, we extend the same concepts with a more rigorous mathematical treatment. So molecules exert an impulsive force on the wall when it collides and bounces off the wall. So pressure is force per unit area. Okay, at this point, I would like to discuss how we obtain averages using graphs. Figure 1 shows the velocity against time graph of a particle. So the average velocity is given by displacement divided by time. So we know that the area under the VT graph is the displacement. And this is the blue shaded area. So we can define the average velocity. And it is a value such that the displacement is given by the red rectangle. So the displacement will be equal to the average velocity multiplied by time. So the whole idea is to get the red triangle, area of the red triangle to be the same as the area under the blue line. So this relationship is true even if the VT graph has an irregular shape. Next, we'll look at the derivation of this equation. Pressure equal to 1/3 rho C square. So step 1, the main thing you need to understand is the way we define velocity using c. So the u is the x component of the velocity, v is the y component, and w is the z component of velocity. Okay, for step 2, we assume that the collision with the wall is elastic. Therefore, the change in momentum will be equal to minus 2mv. So the magnitude is 2mv. Okay, step 3. Now, the important thing about step 3 is to find the average force. So let's take a look. The area under the force against time graph is the impulse or change in momentum. The total change in momentum is the sum of all area under the blue triangles. This area is also the same as the area under the average force times time graph. Okay, that is the area in red. Each rectangle represents a collision. So the time interval between collisions is delta t. So average force is equal to total change in momentum divided by time. It's also equal to the change in momentum for one collision multiplied by the number of collisions divided by time. So with this, we are able to get the average force equal to mv squared divided by L. This is what you have in your lecture notes. If you have n particles, then the average force must be multiplied by n. So you sum up the change in momentum for all the particles. So step 4, we have pressure equal to n m v squared divided by volume. Okay, step 5. The main thing about step 5 is to be able to relate v squared with c squared. So v, remember, is the y component of the velocity, and c is the velocity itself. So with this, we are able to get equation 1, and from there, we'll be able to get the relationship, the equation P equal to 1/3 rho c squared, where rho is the density of the gas. Molecular interpretation of temperature. The relationship Ke equals to 32 kT is provided in the A-level formula list. So you need to know how to use this equation. Let's look at lecture example 6. So the average velocity is 0. Okay, the velocity has a negative as well as positive. Negative means one direction and positive is the opposite direction. So speed doesn't have direction. So that's why the average speed is 1.53 meter per second. The root mean square speed is first you square it, then you find the average, then after that you square root. You get 1.85 meter per second. So here we have the example to show us how to find the average velocity, average speed, and the root mean square speed. Why are we interested in root mean square speed? So we know that kinetic energy is half mv squared. So the average Ke will be half m v rms squared. So it is not half mv average square. So we are interested in the root mean square speed because it gives us the kinetic energy correctly. Lecture example 7. For a monoatomic ideal gas, the internal energy is 32 nRT, and that is 7,300 joules. Part B, the average Ke of each helium atom is 6.07 times 10 to the power of minus 21 joules. So with this, we can get part C. So looking at the derivation, you should be able to obtain the amount of energy added to the system is 21,900 joules. With this, we come to the end of this topic on the ideal gas.